everyone. Welcome, welcome. We're at our second to last day of the AI summer. We've made it. So we are going to pause for just a little second. We have a minute before we actually start, but we might pause a few more minutes after that just to make sure everyone gets here. And as you guessed, oh no, it's me, the person who makes you type a bunch, makes you use the workbook. And so I tried not to do it, but I had to. So I added the workbook this morning in case you wanted to type with me. But you don't have to. You can always just use the solutions directly. All right, we'll just wait maybe a minute or two for everyone to come on in. All right, and I'm just going to go ahead and while we're waiting here, while we're paused, I'm just going to go ahead and add our AI summer repository, our old pal there that we've seen a lot. We'll be using it some more here today. All right. Maybe give people one more minute to come on in. Oh, and their women is open. Oh, it seems like people are still filtering on in. Give them a couple more seconds here. Let me add that back in there. All right, well, I think this is a great time to get started. Welcome to the second to last day of AI Summer. Today, we're going to be continuing with what Abby started us off on yesterday with training of these large language models. Yesterday, Abby told us and taught us a little bit more about what it is to use inference with Hugging Face with our large language model or with our language models or large language models. And so what we learned was that we could use these Hugging Face pipelines, which would do these different tasks for us. But also we learned that we can train models. Given our API tokens, we can push our models up to Hugging Face and share them with others or not. And we also have data sets that are available for us to use through Hugging Face. And today we're going to build on that a little bit more. We're going to do a little bit of tying everything together today. During the first week, Jesse gave us a really great introduction of large language models, what's going on with generative AI, the ChatGPTs, the GPT-4s. And now we're going to revisit some of those same resources again, now that you've seen a little bit more and use a little bit more with our transformers and with our generative AI. And then we're just going to expand upon and go to stage 2 of what Abby talked about yesterday, and we'll talk about training of these large language models. Okay, so before we jump all the way in, any questions? Right, Raymond.
I just had a brief one. I didn't notice it in my emails, but as you add new Coursera courses, is that something that you either are and I missed it or intend to include in the newsletter? Because there's Dr. White's is the only one showing at the moment, and I was kind of curious. Jesse had said something about more things being added later on. I know I personally would be interested in when those were added to Coursera.
Jesse?
Those will definitely appear in our newsletter. So for example, later on in the summer, we'll be creating, closer to the end of the summer, we'll be creating additional workshops, especially for faculty on the use of generative AI in their classrooms. And then we'll certainly be putting together our workshop series for the fall as well, which will begin in August. So those will all definitely be on our newsletter and also on our webpage on our events and workshops page.
All right, fantastic. Other questions? Wonderful. Well, let's jump right on in. So I am going to share the repo just one last time in case you need it. And then I'm going to go ahead and share my screen. which somehow is still hard after all of these years. Let's see, which one is it? Let's go with this one. Ah, got it. All right, so here we are. Today, we are going to be working in these 4-2 notebooks, okay? And again, I know that there are different learning styles represented here. Some people like to type along, some people like to execute the code and just kind of look at it. If you're one of those type along folks, join me in clicking on this this notebook with WB at the end. It just stands for workbook. Otherwise, you can feel free to open the solutions. You can open the solutions at any time in case that just has all of the full written code. But I'm gonna work in this workbook and hopefully you'll type along with me. So we're gonna go ahead and open this one up. As we know from all of these weeks, this is just something that we look at. And so we're gonna open this in Colab, which is gonna give us a nice kernel for us. Something to know before I start using Google Colab. So I'm on Google Colab Pro, as you can see. There could be a moment when we are training these models where your Colab is like, look, I'm out of memory, like it's too bad. So if that is the case, just do know that you can get a subscription to Google Colab Pro, which would enable you to do the training of these models, because I just gave one a try earlier today, or no, like earlier this week, and it worked great. So just know that. Okay, so today, as promised, okay, we're talking about supervised fine tuning and reinforcement learning from human feedback, okay? So we've talked about that a little bit already, but we're gonna dive into it a little bit deeper today, but still sort of at a high level, given some of the intricacies and the newness of some of these methods. We're gonna be talking about supervised fine tuning. And so something to know about some of the jargon that we're going to talk about today, it is just like being abused like so heavily. Like the same word that we use to talk about like fine tuning a pre-trained model is also applied to fine tuning in a different sort of way, and like not really a pre-trained model, but a pre-trained after the pre-training with the fine tuning and then more fine tuning. So do know that you're going to have to put on your, Transformers hat and really pay attention to the context in which these words are used. Because they will have different, they have the same meaning, but they are applied in different parts of the process. So today you're going to learn all about that: supervised fine tuning, instruction fine tuning, reinforcement learning from human feedback. You'll also learn a little bit more about what it takes to train these models. We'll learn a little bit more about the data, how humans are involved in this. I know there've been a lot of questions about that. And so also there's a paper that I provided here today, which will allow you to investigate that at length for OpenAI's models. Also, we'll go through some of the code that's needed, and you'll see some of the compute resources and experience that. And again, the code is provided here for us to use. So let's start by just installing our packages that we're going to need. We'll talk about what these are later, but you already know Transformers, that's coming from Hugging Face, and data sets, which is also coming from Hugging Face, which gives us access to all of this great functionality that's offered through Hugging Face. These last two are to help us, one with training and another type of reinforcement learning training offered through Hugging Face. Okay, let's run it. Okay, we're gonna run anyway. Great. So now, okay, so I think at the very beginning of this course, if I remember correctly, we saw a particular blog post by Hugging Face, and Jesse introduced us to this. And the blog post was called "What Makes a Dialogue Agent Useful?" And actually, I'm going to go ahead and open up my chat real quick, because I hope you will chat with me a little bit more, or just feel free to unmute and we'll chat. And so let's go ahead and click on that so we can explore it. Hopefully, great, it opened perfectly. So I think this is something that Jesse shared with us. If not, he shared it during the class, and so, or a previous class, and so I thought it was awesome. So this is a great document to read. It's coming from Hugging Face's blog. I'm going to go ahead and recommend that you spend some good time on that blog. It has great stuff, great information about ethics. It has diffusion, model training, all of those types of things. Just great articles to read. But here we're going to kind of skim through this together. Whenever we were talking about this paper, okay, we were talking about some of the models that were available at the time. So here we are, we're some months later, okay? So there are things that are already kind of out of date with this, but we can still take a look at it and use it for what the great resources that is. So one, we saw that there were a number of models that were available or would be available even at that time. And this table tells us a lot about how they were trained. Okay, but the article tells us even a little bit more. So we can see here that we have these different models by these different organizations, how they're accessed, and their general size. Take a look at that, because some of them are bigger than others, but we can look at how that affects the performance at some other time, and it's also kind of in the model cards. Also, we can also see the pre-trained base model. Yesterday, there was a question about which base do I use? So that is a really great question. And again, it's going to depend on some of your knowledge of the internal working of the model, if that's something that you're focused on. Otherwise, it's just going to depend on your experimentation and the sizes that you're able to accommodate in terms of computed training, if that's something you needed to do. Also, the data that it was already trained on, even though these super large language models have been trained on so much data. We can also see the data that we were talking about, this pre-training corpus size. We can see the differentials around here. So one, we've learned something important, which is that we have to do some sort of pre-training. Okay, so we understand that. We know to make our dialogue agents useful, we got to do some kind of pre-training. Do we have to access the web? Well, not necessarily, but it is nice, as we've seen. Do we need to do supervised fine-tuning? So across the board, everyone is doing this thing called supervised fine-tuning. So depending on how much you know about transformers, this can mean something or it can mean something else. They mean something very specific by that, which is what we'll get into a little bit later. Then they go into this fine-tuning data size, which is like in our minds, we think, okay, these are kind of encompassing similar, if not the same things. And here is where we see a lot of what they mean by the supervised fine-tuning. So you can see that there's specific things for some of these models that they're looking at in terms of the data size. So this quality part is going to reflect the part of that fine-tuning data set that is trying to get at fine-tuning for quality or safety or groundedness. And you can see that there are some different types of data that are kind of wanted in this fine-tuning for these different models. Some of these, we just are not really knowing what the data size is. We also see that reinforcement learning from human feedback is also popular in some of our models. That might be something that we want to use. And there are also sometimes some handwritten rules for safety. So this offers us some other methods that we might use to have kind of safety imparted into our models. And we can also talk about that more when we look at the OpenAI paper. This is also an interesting area that we need to decide, or there needs to be some decision around how we are going to evaluate the performance of this model, of these models, because it's hard to say, like, in terms of okay, which ones are better than, like, which responses are better than others. And so these are a number of the criteria that these different models are using to evaluate which answers or which responses are the ones that one might consider to be better than another. Lastly, yesterday, I know we had some talking about the human aspect and the labeling necessities provided or required for supervised fine-tuning and for reinforcement learning from human feedback. Here you can see how those labels were created a little bit, but something that we learned from this is that the labels were created by generally people. Okay, so people did all this work. We talked about how yesterday there was some issue with some payment with this human labeling, but that's something for us to consider as we go along with our model training. Okay, so where are we? We said we need to do some pre-training for sure. Otherwise, we're not going to have a language model at all. It probably has to be really big. So if we're training it from scratch, this is the size data that we need. Then we need to be doing some supervised fine-tuning, whatever that means. We will likely do reinforcement learning for human feedback, and we'll need to have some evaluation criteria. But we will also need humans or some method of human intervention to tell us which answers that we would prefer from the model than others. So that already is just sort of telling us something. Okay, so now we're just going to scroll down again. Like, would have been nice had I sent this to you yesterday so you could have read through it. But let's talk a little bit more about these individual pieces. So one thing that we have seen is this necessity for instruction following. We all like that, right? in our AI coding session, our AI coding week, we wrote a lot of write the code that would allow me to blah, 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 write the Python code that would blah, 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 blah. And so what we want is this model to follow the instructions. And so that's not something that the model can just really do by default. When you're training your large language models, again, sorry, it's going to be a scrolling kind of day, so hang in there. So when you're training your large language models, that we said before, with this one, with our pre-training, we are predicting the next token. You know, it's just it's a relationship that we're learning, but it has nothing to do with instructions, nothing. It just means that we're whatever is in this training set coming from the internet, we're just predicting the next token over and over. So we're having a sense of English, the styles, what kind of words flow together, but we have no idea about instructions after we've done that initial pre-training step. So that just creates our large language model. Now we have to make it useful for us. Great way is instruction following. Let's scroll down, let's get it. So instruction fine-tuning. This is generally how we will get to the point where we will have this model that is able to follow instructions. So again, we have this task that we want it to do, and we as humans would want to give it an instruction, and then we might have some input, but we want it to give us some response. And so we provide these demonstrations to the model, and so it trains based on these instructions, so it's able to follow the instructions and generate the outputs that we would want. Again, they tend to be human written, but some data sets are out there that are essentially synthetic or generated sort of by kind of models. And so as you can see here, there are some different data sets that we have that range between how much a model or a computer has generated versus how much humans have written. So do take a look at this. If you decide that you need to do some instruction fine tuning, you have some options available to you. Some are available on Hugging Face that can help you with this. And if the link is, if getting where this is, so if you go back to this notebook, you can see here, you can click here and this should open for you. All right, scrolling on down. So one, we just learned about instruction fine tuning. We love that. Okay, that's going to help us actually follow instructions. So we started with pre-training, we got our language model, we're understanding grammar, we're understanding a little bit more about semantics. Now we need to make it useful for us, right? So now that we've made it useful for us to be able to actually follow instructions, that's when we did our instruction fine tuning. Okay, so another step. Then we have, okay, this idea or this necessity, especially if this is going to be distributed on a wide scale, that we actually want the instructions to be helpful and safe, right? So we don't want them to be overly offensive. We don't want it to be generating these terrible ideas that someone might put into law, for example, in Florida. We want them to have these helpful and safe responses. And so to do that, we can use supervised fine tuning. So again, so this is the context in which we're using the phrase supervised fine tuning, which is together with instruction fine tuning often. So they're kind of two parts of the same thing, but usually supervised fine tuning is going to reflect this desire to have these responses that are actually conferring something that's helpful and safe. Okay. So then we have, in addition to our instruction fine tuning, we have these examples that are allowing us to learn the better or the more helpful, or allowing us to learn helpful and safe responses. So again, we are creating these. Lastly, we have another fine tuning, which is reinforcement learning through human feedback. So with this, we have a decision. So it will be a reinforcement learning. So what is that essentially meaning? We have this model that is taking in these texts, and then it is returning some value, which is reflecting the reward associated with that particular goodness of a response. And so we have a model that does that, and then we use that model to train our other model, our actual model, based on what we have developed as humans. And so that was a little bit confusing, but we're going to get into that in more depth in a second. This is just a high level view. Okay, so again, what we want from our language models is more than just this model that predicts the next token. We want it to be able to follow instructions. We want it to generate instructions that are good. And we want it to generate instructions that we want it to generate responses that we actually like. All right, so let's summarize that real quick. So we're going to come back to this. It's time to type, people. Sorry. All right, so now let's just overview. So what is it? So what did we learn? Okay, so we learned some things. Let's just make sure we got it. So one, we learned that we need to pre-train the model, or we need to have some sort of pre-trained model. And we need to have data that would make that possible, right? So either we need to train it from scratch. I'm talking scratchy scratch. What does that mean? The weights are random. If you were to put an input into this model, what would it generate? A bunch of tokens that are just completely nonsensical because it has no idea the relations between any of these words. Our pre-trained model is going through and it's learning concept of grammar and syntax essentially. So we need this pre-trained model, or we need to train it, and we need the data to do so. What else? We need human people to help us. So we need some type of human intervention, advice, labeling, annotation, something there that's going to help us to generate preferences and instructions. And examples. So what are we using those for? We're using those for supervised fine tuning, namely the SFT for safety, and then the instruction fine tuning. We're just going to call that IFT. So it'll actually be able to do the things that we want it to do, and then also do it in a helpful way. Then we may want, and we probably do want, to have this reinforcement learning. We're not going to type that whole word out. Reinforcement learning from human feedback. And so that is going to help us distinguish and learn the policy that guides us in creating, guides the model in creating the responses that we actually want. Okay, so excellent. Okay, we're on our way. All right, so this is what we just said, right? Sorry, I made you type it. So here are our steps that we just said, right? Pre-training, scratch, training model, big data set, supervised fine tuning, which is going to include following instructions and making it safe. Then we're going to have this big old long reinforcement learning training thing so we can get this reward/preference model that is going to tell us how good a response is. And then we're going to have this reinforcement learning from human feedback, which is we're going to use this reward model to help train our own model. So this is the overall view of this thing. Okay, so this is provided by OpenAI. They have really just great visualizations of this. Here we can see the individual steps, right? Except for this is kind of missing this step 0. So there's a step that comes before this, and that's the full pre-training. Okay, so we're going to assume that we're already at this pre-trained point where we have this thing that does pretty well in predicting the next token. So then where do we go? We need to generate this really large data set, not really large. It's pretty large, but not as large as the pre-training data set. So we are going to have this data set, which is going to be a set of instructions or safety demonstrations, a set of prompts, and then we're going to have these labelers, which are going to show the desired behavior. And so we're going to see an example of that a little bit later, but essentially you have a prompt and then you write the answer which you would want. And then we're going to use that in our supervised fine tuning. So this is what our supervised fine tuning is going to look like. This over here, these two things here, are our reinforcement learning from human feedback. So this here is the creation of our reward model. So here, OpenAI has a particular way that they are doing this and to create this rank, but the overall goal is that we want this reward model, which is going to take in the prompts and outputs, and it's going to output a scalar value, which is reflecting the reward. Okay, and then once we have this reward model, and so it's very interesting because, anyways, we'll get to that. So once we have this reward model, we can use that to help us to train our original model. And so now this thing right here is called the PPO model. And so we are using our reward model to generate the output. Or train our model to generate according to the policy, which is going to be outputting what we actually prefer. And so to look at that in a little bit more depth, we can look at this. This is an exceptional paper. This is actually coming from OpenAI. And it is coming from their their findings from ChatGPT and I think, ChatGPT. So GPT-3, GPT 3.5. And I would, again, highly suggest you take a look at this and read this sort of in depth. It tells us about a lot of things in terms of the things that we would want to think about in terms of training our models. Again, especially if they're going to go to a lot of people or be used by a lot of people. So I know a lot of researchers here are talking about models like for themselves to generate parts of books and things like that. But if this is something that would be used by the wider amount of society, then OpenAI does have some really great statements and guidance on how one can think about embedding that kind of information in the model. And it also talks about how they specifically did that. So this particular model is talking about fine tuning, or this particular paper is talking about the whole training set space, but particularly the supervised fine tuning and the reinforcement learning from human feedback. Oh my gosh, that looks really, really familiar from what we literally just saw. This is where it came from. So this is, again, the steps that they're describing. These are their initial findings. Give them a good read. This talks about more in depth about training language models. This talks about harms. Very interesting in terms of things for us to think about as we are creating language models and how we can fix those things. This is also talking about the composition of their data sets. So if you're thinking about creating your data set, then you might want to look at this and look at it in the context of the performance of the models that we see. So again, we have how they have described what they have done. For some more jargon here, these are really great in terms of understanding what types of prompts that are generally used. I'm trying to find what I'm actually trying to show you. So this particular piece, this human data collection part, this will tell you about how people were generating their, how people were used to generate the prompts, and how they used the data for that, and then how they cross-validate, or how they validated that with the general public. So this is also helpful just in case you want to learn a little bit more about what our models are doing, what their models are doing. And so, yes, and so here is, this is just a really great, really great paper on to guide your training of your models. Lastly, we can also see this evaluation. And again, here we are again trying to figure out how the model is doing, because it's hard to have like really a metric for this. This is the way that they choose to evaluate this. And we talked about like honesty, harms, and things like that. So here you can see a lot of their results at the very end of this. So this thing is 68 pages. They have lots of appendices that are just fantastic in terms of understanding what their like data sets are looking like, some of the prompts and things like that. So this is absolutely, give this a look if you want to create something like your own data set, or train these models more in depth, or just simply understand what it is that OpenAI has done. All right, so thus far, okay. What questions do you have? Because we're going to go a little bit more in depth in each of these areas, but not too much more in depth, just a little bit more in depth.
I'll just mention that life comes at you fast. There's a paper released today that seems to indicate that you might be able to get reinforcement learning from human feedback type behavior while not using reinforcement learning. And it was mathematical proof that the cross entropy, defined in a particular way, you could actually use a categorization task. So this part right here may get a lot easier soon, but we'll have to see.
Life does come at you fast, huh? No, that's really awesome to learn, because so as you all read through these papers, particularly this reinforcement learning one, we'll get to that at the bottom. It does seem like sort of a lot, and there's like a lot of optimizations that are used because they're using like the same model. They're both big models. And so a lot of people have done optimizations, but it's great to know that there's like a reconfiguration that's on the way. That's absolutely fantastic. All right, so now coming back to pre-training. Okay, so I've just provided some resources here for you to read through. Okay, so this comes from here. So if you want to read more about that, just to refresh your memory a little bit, disambiguate. Also, this is the original paper from OpenAI, maybe not the original, but this is when they talk about their pre-training strategy, as well as a different kind of fine tuning that we used to do back in the day last year, where we'd fine tune the model head for specific things. But just a quick reminder of what we are looking at. All right, so this thing right here is, depending on how you look at it, we're going to choose to look at this as a decoder only model. Okay, so we said transformers, the full transformer can be an encoder, decoder architecture, an encoder, or a decoder only, right? And so we're going to choose to look at this particular transformer. This is going to be a decoder because that's what our generative AI models mostly are. They're decoder only. Okay, so we're going to be looking at this. So as we see here, it's exactly what we expect, right? We have our input, it goes through our transformer, right? And we get the hidden states out. Purple things are like things that are not really part of the model. They're kind of outputs or inputs to the model. We get our hidden states. Those hidden states go into some sort of head. Okay. So what did we say that we liked about these transformers? Many, many things. One of the things of which is you can do this pre-training where you're training essentially this part of the model. You actually have the whole one, but you're training this part of the model so that you can actually attach different heads to it and then train whatever new thing that you want. So let's say, for example, you start off with a GPT model. This GPT model has a language modeling head because that's how you train a language model. So at any given time, it's predicting the next token. Exciting, exciting. Those things are exciting. We train it, it's awesome. We could choose to chop off that little language head part and put on a different head. So we could choose to put on a classification head if we wanted to. We could choose to put on these different heads. Okay, will it actually be good? Don't know, but we could choose to do it. And so because there's so many different kinds of models, why is that really nice for us? Because we have this language modelness, the semantics-ish of certain words. We have this pre-trained network that we're always have available. And because we're only really switching in the head, which is just a lot less weights than all of this transformer network, that means we need fewer examples to train a whole model because most of it is already trained. Okay, so we love transformers. This is what it looks like. Again, remembering that this is our transformer body. We get hidden states out and it goes into a head. That head can be decoder, or it can be a language modeling head. It can be a sequence classification head that we saw yesterday. We can have translation. So we can have any number of heads that are of interest to us, and we can switch them in and out and then train the model a little bit more so it actually learns the task, which is defined by the head. Okay, so this is what we learn. Pre-training. So when we are pre-training in this context for generative AI, again, we have the same exact thing. Again, one more time. This is our transformer. We have a GPT decoder only architecture. The head is going to be a language modeling head, which is a causal language modeling head, meaning that it is predicting the next token. And this is how we are training our model. What's exciting about this is, again, we don't actually need any labeled text because the data itself is providing the labels. Why is that? Because if you have a full sentence, that means you can always predict the next token of any individual, of anything that comes after the first token. So now we know that we're going to be doing some pre-training. Again, if you want to learn more about how OpenAI has done this, here's the paper. So then we get to this supervised and instruction fine-tuning. Okay, so this is precisely what you would think, right? So we have already sort of talked about that instruction fine-tuning is another set of prompts, but they are prompts that are allowing the model to understand instructions. So let me see. I can't remember what I linked anymore. Let's see. So here is just a side note. This is a self-instruct paper. So this is just describing the approach that some researchers took to generate alpaca. So this is like self-generated instructions. This other unnatural instructions. So that sounds like really funny and weird. But this is a data set that is basically generated by like not by humans. So this is though what our instructions and our instances are looking like. So we have some, so you might have some instructions and then you would have whatever outputs that you actually, so instructions and you get the actual. So this is what our instances are sort of looking like. So this is different from our pre-training text, right? So our pre-training text was literally just any text that come from a book, didn't have to be instructions. These are specifically instructions. And so we're doing the same exact thing actually, but we're doing it on this different data set that is specifically about learning instructions and learning how to respond to instructions. So exciting. Then we have reinforcement learning from human feedback. And so this is also a really great resource. This Hugging Face blog, once again, this talks about reinforcement learning from human feedback in depth. And so it talks about the different ways that we go of, not the different ways, but it does talk about some different ways taken by different organizations to train their reward models. But take a look at this, read this a little bit more. Essentially, it means that we need to have like the scale to reward, and a separate model is going to be actually training that reward. And then we use that preference model to train our original model. And here is a full example from Hugging Face, again, from the blog. You can see it top to bottom. It is a little bit awkward to just keep on scrolling, but we'll get to the coding in just a moment here. This is Stack Llama. Okay, so what is that trying to mean? So this is actually going to be a full reinforcement learning walkthrough for coding though. So it's going to use Llama, but the point is going to be use this with some actual coding. And so here you can see what this looks like. Again, we have that same supervised fine tuning where we do instruction following, and we're making it helpful for us. And then here we also have this ability to actually get the responses that we want. And this, if you want to, you can try the actual Hugging Face space that has been provided to kind of interact with this. But essentially, maybe you should just, maybe it would be better if you just went through this on your own, give it a good read to try to understand a little bit more about reinforcement learning from human feedback and how this is trained. Here you can also see, okay, what we're talking about in terms of some of the optimizations that are taken when you want to do these types of trainings, because it depends how you train them. Some organizations take the language model, like the actual language model they have pre-trained. Essentially, they have a copy of it and they use that to create their reward model. And then they go back, and so now they have these two really big models. And so other organizations are getting around that a little bit and taking other approaches. As we said, the field is developing, but it takes a lot of compute to be able to try to get through some of these things. But as we saw that Jesse said, maybe we won't need to do that as much anymore. Also, people have some other ways of doing the reward modeling, which we'll see a little bit later when we start coding. All right, so, okay, thus far, do you have, or what questions do you have thus far? All righty, well then it is time to code. It is that time. Okay, so actually, okay. Let us take a 5-minute break. I know it's like very early, but let's take a 5-minute break. And then we're going to use the rest of our time to get through this code, because it could take a short period of time or a long period of time, depending on how we do this. So let's just take a quick 5-minute. Actually, it's going to be a little bit more than 5 minutes. Let's come back at 9:45. Okay, so I think that's 7 minutes. And then we'll use the rest of the time for this coding part. Does that sound good? All right, fantastic. 7 minutes. See you soon. All right, welcome back, welcome back. Let us get into the coding. There is a really great question in the chat from Victor. It's saying, is the output from the pre-trained model input to the head, or does the head become part of the pre-trained model's architecture? So both, okay? So we will see what this looks like, but essentially, oh, I'm not sharing my screen. How do I never know which one it is? Ah, there we go. Oh, where'd the chat go? So this is the pre-trained, this would be the transformer part of the pre-trained network, which will always output hidden states. And so really the hidden states can go into sort of anything. So this head could actually, I mean, you can use the hidden states just directly and then train some other model from that. So in Hugging Face, I'm going to try to answer this question, and please let me know if I don't answer it actually. So in Hugging Face, what you will see is, actually, let me just show you in Hugging Face. Okay, I'll show you. And it will actually be super soon. So now we're going to start with part 1 of what we've learned about fine-tuning large language models for our purposes, which is going to be pre-training. So we saw actually this yesterday to some extent. Again, yesterday we talked about inference, which is if we have an existing pre-trained model that we can pass the inputs through this model to get an output. And so that has nothing to do with training. It's just getting an answer from the model. Here we're talking about specifically training. So what does that again mean? It means we are changing the weights of the model. The weights fully define the model. Okay, so that's what the weights in the architecture. So the weights are the things that we are changing to train the model. Okay, so now we are changing things in the model as opposed to inference when we are changing nothing. We are just passing the inputs through the model. Okay, so now so make sure you've run this at the top. Sorry, we're scrolling here. Make sure you run this because again, we need this. We need these packages in our space. And so when it comes down to any individual person here who might be thinking about fine-tuning their large language model, you might not need to do any pre-training, or you might need to do some pre-training. It depends what you need. So one, if you have your own data, this might be a great moment to use that data. Also, there are lots of data sets on Hugging Face that you can use to pre-train your model with a little bit more information. Also, you can take a look at, so this is another example of a data set. This is actually, I think this might be instructor. No, this is another data set that you can use. This is Red Pajama. And so this has lots of data that you can use for any of your particular, predict the next token, lots of token here to predict, okay? So fine tuning or pre-training, you got it. So then the second thing that you need is you're gonna have to have some model. You got to choose the model. There are lots of models, as we said before. Here, I'm actually going to come back to this thing that I've opened. This is Hugging Face models. So there again are lots of models that we can pick. If we go down to natural language processing here, we can see that we have text generation. There are lots of models that you can pick to do text generation. It is also important to actually look and try these models. Some of them will be doing different things. So just keep that in mind to train on different data, but give them a try. Give them a try, whichever seems to float your boat. And then we can use Hugging Face, as we know, to help us with this. So let's run this one. So what are we doing? So again, we are training, pre-training, so we need data, load data. We need the pieces of Hugging Face tooling to help us actually do our training. And then we need to do some sort of evaluation. So we can actually do that. So let's import this. These are our imports that's running. Here, we are actually going to download these pre-trained models. So these are already like pre-trained. So again, we're abusing this notions of pre-trained. So this is from pre-trained because it's already pre-trained. So it already has, these are not like random weights. These are already kind of model weights that are already like sort of good, but we can train them some more. And so now we're going to have a second layer of pre-training so it can fit in the methodology that we described. So we're just going to train it some more. So what we're doing is we're getting a tokenizer for GPT-2 here. And then we are getting GPT-2 with a causal language modeling head on it. Okay. So then I think we've seen these errors before where it's like pad token ID has been set to blah, 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 blah. We'll talk about that a little bit more. But essentially, if we want to get rid of that error, we can just set the pad token to be equal to EOS in end of sequence token. This has substantial impact on how your model stops generating text. So at the end of this, we will talk about other ways to do this where you actually have a real EOS token. Yes, so let's run this one. This is going to download all the things that we want. Excellent, exciting. We're getting our model, we're getting our tokenizer, we're getting config, we're getting all that great stuff. And we are getting it right off of Hugging Face. Got the model, great. All right, now to answer the other question. So someone asked about the head that's fine-tuned. How does that work? So we can look at this. So this is the model. So I'm just going to shift enter to run this. So here you have GPT-2 with the language modeling head, right? Here goes your actual transformer. So this is GPT-2, like the transformer part. And then you have the language modeling head. So this is something that you just kind of, you can just add on. You can also remove it because it's another layer and then put on a different head. But you would still have all of these weights and all of these layers. That would be the same. Okay. So it's pretty exciting. Does that answer the question? Okay. So now we have this model that we're really excited about. And now we're going to take it all the way back. We're going to take it back to the second week of coding. And we're coming right on back to this 20 news groups. We're just reminding ourselves how we can use custom data. Okay, so again, I know people here are interested in using their own data. So we're going to walk through what this looks like. So this is just some tar file that is stored somewhere online. We're just going to like go grab it and we're going to untar it. So let's run this one. So here I just switched this over to the file view. And so here you can see that we grabbed it, downloaded it, there it is. And here we have untarred it. Here we can refresh and we can see that we have our data here. Again, once you close the session, all of this is gone. So if you need to download something, like make sure you download it before your session ends. Again, we can see here that we just have all of the data that we're interested in. These are individual files. Okay, and what these are specifically are these emails from, I mean, it's just emails. This is a pretty strongly known data set. So these are just like emails on like a news list or something like that. All right, so now we have some data. So now what we're going to do is we are going to load this data and make it into something that we're going to actually use with Hugging Face. Now, yesterday, people had some questions about what's going on with this data set situation. Okay, let's talk about it. So one, looking at this, what we see is we have what we've done here is essentially, we're just reading this in, right? So we have the path here. We're going to choose some particular directory. Maybe we just want to train on this particular directory of information. What we're going to do is we're going to get those files. So it's going to be 52, like these file paths essentially, and we're going to create this empty list. Then what are we going to do? We're going to go through all of those files. So for each of the text files that is going to be in this list here, we are going to essentially open that file. This right here, all it does is it puts together that base path with whatever specific text file that we're looking at to create the file path. We're going to set it in read mode. And we do need to specify this in coding because for whatever reason, these news groups are just like, the data is just not in the standard UTF-8 encoding. So again, we are reading a particular file as F, and then all we're going to do is read that file. It's going to return us the text of that file, and then we're going to append that text here. So let's run that right quick. All right, so we've made it there. Okay, so, oh, okay. So we can see here that we have text. So this is a variable inspector. That basically means like we can look at the variables that we have in our kernel, right? So here we have the actual text list. We can see that it has 981 items. Exciting. So this, oh, I did not know we did that. But here we go. We can actually see what we have. All right, so this might be similar to you. You might have lots of files on your computer. You might upload them to Hugging Face, or you might serve them up on some website for you to download. You might have them as a tar. You know how to do that. You can download, you can untar, and now you can read all the files. Now, the question now is, what's the easiest way to get this into like a data set format? Before, so yesterday we saw that essentially we downloaded this, we called like load data set to load our data set from Hugging Face. Now we're going to make the same data set structure. When I talk about data set, I'm talking about a very specific Hugging Face class. And so we're going to make this data set structure. How can we do that? All right, well, let's look at it. So one, we see that we imported this function or this class called data set. And I also imported load data set for some unknown reason, but we're going to use this. So this data set here, that's what we're going to use to create a data set. And we're just going to type it right here. We're going to call our data set HFDS, and we're going to use that data set class. And what we're going to do is we're going to create this data set structure, okay, this object from a dictionary. A dictionary of what? Well, number one, we know we're creating a dictionary, so we need the curly braces. What is our dictionary going to be? Well, we're going to write essentially individual columns, right? Where each row is a particular example. So for a particular example, you have field 1 describing it, field 2 describing it. So what does that mean? We can have a column called file. And then that will be a list of the file names, for example. And so that could be data files. And then we could have another column, which would be what? The actual text, right? So text, and it's going to be the actual text. So that's exciting. We're actually just going to go ahead and run that one. We're going to run these kind of like over and over. It's not going to make like a big difference, but so, okay. So now that we have that one, we just printed this one out so we can see what it looks like. It is this data set structure, right? And now it has that file thing that we had. So all the data files, and then it has the text that we have. If we wanted to look at any individual one, we could do that, and we'll do that in just a moment. So now that we have this data set, you see that it's just like one big data set. Something that you may want to do is just like split the data. This is just an example of how you go and do that. So what we're going to do is we're going to not update, but we're going to essentially create a new instance of this data set, which is a split data set. So we're going to do a train test split, where the train size, we're going to just set it to be 0.8. And again, you don't actually have to do this, but it is nice to see often the evaluation on a separate data set. If you don't have enough data, you don't have to split it. But we're going to split it just to show it. So here we're going to run this again. Here you see the difference between the original Hugging Face data set that we had versus after we had this train set split. You can see here that we have a training individual data set and a test data set, and they are lumped together into a data set dictionary. Now, why is this pretty exciting? The reason is if you want this to be reproducible and you want other people to be able to use your data, this is how you can distribute the data as this data set dictionary that's already split into train and test. So if someone else is going to compare the performance of their model against yours, they can use the exact same data. So we have this data set, we have data set dictionary, we have a train split, we have a test split, it has the file, it has the text. Let's just make sure, sanity check, to make sure that it actually has the data that we want in it. So we're going to look at the train split. And let's just look at a particular example, maybe 0. And there we go. So this is what our data structure looks like, right? We've just created this. So just remember this, right? So if you have your own data, what you need to do is make it accessible in Google Colab. That could mean dragging and dropping it over here. This could mean downloading it, tarring it, curling it, whatever. Then what you can do is just read all of that data. If you have something that's in a CSV format, you can use different functionality like dataset from pandas, I think, or from data frame or something like that. And you can read it from a data frame. You can also call load dataset directly, and I think that's why I had it there. But it only works. So if you have a whole directory of text files, nothing but text files, you can call load dataset on that directory. And if it sees all text files by default, it'll be like, I know what to do with that. And it'll just go ahead and create your data set. No need for reading in all these files or anything like that. Do the same thing with JSON line. Might be JSON lines. It'll do the same thing with a directory full of CSVs. But we're waiting to write it. This one, we had to do it like this just because these file paths did not end with .txt. So whenever Hugging Face looked at by default, it was like, I don't know what to do with that. That has no file ending whatsoever. Had it ended with .txt, we would have been able to call load dataset directly on that directory, and it would have been like one line instead of all of these. That's neither here nor there, just something to know. Okay, so now we have our data set, right? You can have your data set, right? So you could have read all your files. You could have created this data set just like this. And then you can also create your train test list. Oh my God, exciting. So now you have your data set and now you're ready to train, right? So we saw a lot of this yesterday. Here, this is just written right for you. We need to tokenize the data set, as you recall. So what does that mean? We need to change our actual words of text into some numbers. Those numbers are changed by our tokenizer, which corresponds to our model. So they kind of come together. How are we doing that here? So yesterday, I think we talked a little bit about the map function. Basically, what we have is this function here. As we said before, this function is going to take in one or more examples. It'll take in one or more examples. And then what it's going to do is it's going to call the tokenizer on the specific text field of our data set. And then if it is too long, it's going to truncate it. And it's going to return our tokenized data set. All right, so how do we do that in this functional call? Well, we have this data set. We're going to call the map method on it. It's something, again, provided through Hugging Face. This is the function that we want to run. We're going to allow it to batch, even though I think this is not large enough to have a full batch. That's even here there. But we're going to allow it to do it in batches. And then actually, we're going to remove this column because we don't really need it when we're doing training. Furthermore, it'll generate like these warnings that are super irritating. So essentially what we want is to only have the data that we need. So let's run this one. Oh, that did not go the way that I wanted. Anybody see the error? Yeah, we call that file. Ooh, should have called that something different. So what we'll do is we'll just casually, now let's try it. Exciting, we made it. So essentially what happened is I typed this wrong. This one should have called that files, because apparently that's how I had it at an earlier time here. So I needed to change that to be file as well. So now we have our tokenized data set. If we wanted to, we can look at it. It's just this thing right here. It's just the data set dictionary that we had before. It's just tokenized. We would see that we have like these different fields on it. Specifically the inputs. We saw that we had input ID, attention IDs. And I mean, we can just look at it. Let's look at it. So token DS, we're going to look at it train. And we can see that this is a data set. So the whole thing is a data set dictionary, but we're looking at specifically the train data set. And we can see that the features that we have now been added input IDs. That's the tokenization and the attention mask. And that is what, in case there's padding, you don't want your transformer to actually look at the part that is just padding. So our attention mask is going to say, hey, only look at the part that is actually text, not this padding part that we added in here, so that our data set batch could be rectangular. Okay, so now we have prepared our inputs, we have trained tests. Now we're making our data collator. This is a thing that is on the fly, is going to help us during training. Okay, I'm seeing some questions. So I see this question. Okay, so there's this. Okay, So why are the number of rows 784 and the list is 981 items? So this one right here is just, so here's the full data set. So we split it into a train and test. Our train is going to be a subset of the data. Our test is going to be a subset of the data, and together they make up that full 981. There's another question. How strongly does the model new data? So the question is, how strongly does the model prefer using the data from the new data we fine-tune it on versus using data from its pre-training data? For example, if some news group posts in our data says the earth is flat and no one else in our data refutes it, does it think that our fine-tune? Okay, so this is an excellent question. And people tackle it in different ways. So here is the thing. There's a such thing as catastrophic forgetting, which means that if you fine tune your data or you fine tune your model, sometimes it will kind of forget what it knew before. However, the way that people combat that is frequently they'll just add in like previous pieces of data from or previous examples from their original pre-training data set so that it's more stable on that. Also, this is something that you can correct in a later stage. So here we're kind of talking about this in the context of maybe you have a GPT-2 and you want it to learn how you write grants, for example. This might be a good moment to do pre-training on your previous grants that you have written. A second step to help us with that particular issue with it saying that the earth is flat is our supervised fine-tuning. And so those are where we create examples where we want to make sure that the model is aware that it should produce these particular outputs. And that's something that we can also do with reinforcement learning. Hope that was helpful. Okay, so now, so we've created our data collator. Again, that is going to help us. All data that we fine tune on is ingested by the model for the good. Would you mind asking that one again?
Yeah, my question is, so when we're putting all these new data sets in, is there a firewall? I think we've already answered that before. It no longer, I mean, we're ending up sharing it with the world. Is that not right?
Remember, it's not memorizing, right? And so it could be learning the concepts of, and the question of whether or not individual information gets in there is a separate question. And you do need, if you're training on sensitive data, you absolutely do need to run tests to see if you can re-identify, for example, patient information. This is always a huge problem. If you train on patient information, on patient notes, names of relatives can show up even if you mask the patient names. And so you have to ask and see if you can re-identify a person saying, I am a 50-year-old asthmatic man, who's a data scientist at a university, in Vanderbilt. My name is, and if it says Jesse Spencer Smith, guess what? Then it's, but you almost have to go to that level to sort of see if you can recover. And it depends on how large the model is, how much data you've trained on, as to whether or not it's going to learn the individual details.
Great question. Okay, so let's see, we have our data collator, and this is going to help us with training. So essentially that means if you have a bunch of examples and you need to put it into like a batch, so your model will digest more than one example at a time. They have to be padded to the correct size. And so this is going to help you with that. It's also going to help you put them together. What we need to pass into this data collator is going to be our tokenizer. And we're going to use the thing that we just loaded, which is our GPT-2 tokenizer. And then also, we can look at the API for this thing. But something that is important for this one is that this is a data collator for language modeling. There's multiple types of language modeling, like masked language modeling, which is a fill in the blank task. And so we need to specify that this is not the masked language modeling task. And the way that we can do that is set this parameter MLM, which by default defaults to true. We will set that to be false. So then it can understand that this is causal language modeling. So let's do that. MLM equals false. Exciting. All right. So now our next step, what do we have? We have our data, it's been tokenized. We have something that's going to help us to put the data together. Now we're going to set the parameters of how we're going to do the training. All right, so I left some of these out because we need to discuss them a little bit more, just to remind from yesterday. So training arguments, they're going to set some of the parameters of our training. So one, the output directory is going to be where the model should be saved. So the name of that directory, we're going to call that GPT-2 email, because those things that we have are emails. For the logging strategy, yesterday, I think you had epoch, meaning that after every epoch, then it's going to write some log information out. Today, we're going to do steps to just experience something a little bit different. So instead of it going through a whole epoch and then do some sort of logging, nope, we're going to make it go through a set of steps. For the evaluation strategy, we're going to do the same thing. It's going to evaluate after some number of steps, which can be less than a number of epochs. And then for the save strategy, we're going to do the same thing. We're going to have it save every number of steps. So that's how often it's going to essentially checkpoint the state of your model. So we're going to have it log every 500 steps. Usually I set these, oh, shoot, wait, no. Let's have it do every 100 steps. We're going to evaluate every 100 steps, and we're going to save every 100 steps. And so this right here that I put in here is truly arbitrary. Usually you want to calculate it based on, I mean, the number, the size of your data set, but we just threw 100 in there because we can. Also, we can load the best model in. We're going to go ahead and do that. And here, this is where you may need to set your own values if you're not on Colab Pro. Generally, I start with 4, but there are, I think Hugging Face, in fact, Hugging Face provides functionality to help you decide what the batch size should be. But for now, we can set this to just be 4. And then we'll let this train for 3 epochs total. And then we're not going to push to hub. You can see that before I didn't have any logging in, no API token, nobody's pushing to hub. And so this is actually moot, but I just left it there. And report to just means how we're going to save like the runs of the model. So let's see, let's run this one. Exciting, wonderful. And then let's go ahead and train. So here, we talked about this a little bit yesterday. We tend to like to put the the training part with the actual creation of the model, because when you run this over and over, it will create a new model every time. So you know exactly how long you've been training. But here we're going to go ahead and create our GPT-2 model. And then we're going to set this, even though this is actually unnecessary because we already have the tokenizer that we'll be using. So then for trainer, the model that we want to pass in is that thing right there. So GPT-2. For the arguments that we want to pass in, those are the parameters of our training. We just wrote them, and that's called training arguments. For our tokenizer, we already said what our tokenizer was. We used it before, GPT-2 tokenizer. We really like to have that tokenizer there because when it writes it to file, if you don't have it there, then it's going to try to use a default tokenizer. The next time it'll be like, I don't know what tokenizer to use. So we like to have the tokenizer written in the save strategy here. For data collator, that thing that we just had, the data collator. For the trained data set, it's exactly what you would think. It's this tokenized data set, and it's going to be the training portion. So let's see. That's going to be token DS, the training portion. And then for evaluation, since we evaluate every 100 steps, we're going to use token DS at test.
And Chara, you have a question from Michael.
Yes.
Yeah, I guess I thought our data, training data is already tokenized. Why you specify tokenizer again?
This helps you to save. So essentially every time you save this model, it will also save the tokenizer with it. So if you don't put this here, it won't save the tokenizer with it. And then the next time you load it with something like a pipeline, it'll try to use like the default tokenizer, which may be fine, that may be fine. But otherwise, you kind of want them to save together. Also, I do think there are options. So I think there are options whether to pass in the tokenizer. If you do pass in a data collator, because the data collator actually already has a tokenizer in it. But I always put these two explicitly because I have run into a terrible moment where I did not put this tokenizer and it didn't save the tokenizer. And when I reloaded it, then it was like a mess. So
Well, I guess for our test data, what tokenizer we use the GPT-2 tokenizer as well, right?
yes.
Okay.
So our data, okay, that's a good question. So our data is already tokenized, but this data collator, okay, so whenever we have tokenized our data, I think we tokenized it, if I remember correctly, to whatever size any individual one of them was. And so if you have like ragged examples, meaning that some are longer than others, right? You need to put this, when you feed it to the model, it has the shape of this tokenized data set has to be rectangular. So something can't be 3 tokens and the next one can't be 8, the next one can't be 5. They all have to be either 8 or some other known length. And the thing that does that, if you don't do it during tokenization, that original tokenization that we saw, is the data collator. The thing is, the data collator has to know what token ID to pad with. And so that information is stored in the tokenizer. Okay, let's see. All right, and so now, we run this one, yes. So now it's time. So now that we set that, okay, one last thing. With your last trainer, you saw something that was compute metrics. We passed in a function to do that computation. Here, we don't have it. And the reason is that you would want to compute the metrics in a way that is reflecting your actual interests. So here it would be more appropriate to have like something like either like a different sort of metric or one of the ones that is specifically for like language models, but here we just are not using that here. But it would be better to add something like that in here. You can also use different data sets for your evaluation as well. And so you can compute metrics on those. So let's run this one. So now we're gonna do a little bit of training. Very exciting, having a good time. Wonderful. So here we can see our model training. And Jesse, thank you for putting in that suggestion and that description of how to get to GPU runtime. Because if you're on a CPU runtime, you'll be sitting here for the rest of your life. Oop, just kicked my dog. Sorry, Chicky.
You'll be done around the time that it will be for our AI winter. So.
Exactly. It will be a while. So here we see that the model is, training. You can see how it is training. We told it, we said, hey, we want you to evaluate every 100 steps. We want you to save after every 100 steps. Let's take a look at that. So one, we see this GPT-2 email thing here, this thing that we saved as. We see the checkpoint that we just made it to because we wanted it to save every 100 steps. And so we're just going to get through that. This is so nice because it tells you just where you are in the training. Okay. Very exciting. So while this thing is training, we're going to just kind of ease on down to supervised fine-tuning. So what was this again? So this is reflecting what someone was saying about being able to train it for, I guess, against misinformation or things that you really wanted to know for safety and for instruction fine-tuning if that's something that you're after. So for supervised fine-tuning, then what we need generally is going to be the data that we want it to be able to, with the data where it matters that the model is answering correctly or in the way that you want it for safety and reduction of harm. Okay, so that's what we are after. This is something that you may yourself have to handcraft for your particular application. Also above was linked that self-instruct paper, which is how like Alpaca was pretty much generated. And so you can use that approach for bootstrapping some like instructions that are relevant to you. Otherwise, let's just take a look at Alpaca, which is a data set, again, which was created off of ChatGPT. So here, if we were to look at this, we have the instruction. And now the input is actually, so the input that we would give to the model, like it really doesn't have anything to like choose from. It just has to just directly generate. So this is the instruction that we would give it. It would have no particular input other than this kind of beginning or this kind of empty string. And what we say that we would like for it to produce is this answer, right? So we want it to produce this answer. In that case, what we can see is that when we put it all together, then we have this full text. So this is how this is what the model will train on, something that looks like this. So let's see another example. Identify the odd one out, and we might give it some options, and we see what the output string is. And so here is the actual input text that we might choose to put in. Now you see that this says below is an instruction that describes blah, 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 right? Response, blah, blah, blah. It's very consistent. This is what the creators of Alpaca wrote as the way to formulate their prompt. Also, just as a side note, if you don't like the way that they have phrased their prompts or their prompt template, I think Miranda and Umang have told us about prompt templates. In case we want to make our own Alpaca here, we can do that from just this instruction and input and output. Also, if you go and you kind of ease on over to the lab that created Alpaca, so one, exciting models, but also they have this alpaca farm thing, which is super cute. But they have a different kind of formulation of this data set. And they have different subsets, which are reflecting like the different parts of training that you might want. So for example, you have this preference. And so here is how you might think about training a reward model, these values associated with the preference or the raw preference. And so you might have to read the paper to decide what these different values are. But you can also use these as well. So they also, where's that original one? I think it's this one. This is the original Alpaca. So 52K, and they have these different splits that are reflecting some portions of the data. So this will be something that's reflecting the supervised fine tuning in particular, some of the preference, and then we'll have to figure out what the rest of these are. It may say down here. Oh, that's really. Nope, still too long. Okay, we can get back there. Nope, no model card, unfortunately. Probably will be in the paper. All right, so now that we're coming back here, we see that we have finished our small little training. Do read the OpenAI paper because it is interesting in the way that it describes how much training is required. This one has been trained for 3 epochs. So that means that it's gone through that entire 700 and something data set 3 times. And so here we can see something that we like, which is that the training loss is going down and the validation loss continues to go down. Generally, we would stop training when they start going back up together, or when the validation loss starts going up and the training loss continues going down. However, the OpenAI paper describes that they continue training. So interesting. So just give that a read. But I think what we can see is, I mean, we'll see this a little bit later, but the requirements for training are a lot. They're significantly smaller whenever you're getting into this fine tuning. All right, let's see. And so I would also suggest here with your eyeballs, you can see the training loss and the validation loss. This runs things right here. This actually has like the records of the runs. You can use TensorBoard to look at this and actually look at the training loss and validation loss. Also, if you were to use a compute metrics, you could see the metrics in there. And it's really helpful for if you ever have to present results to anyone to actually show the training curves, because the first thing that someone's going to ask you is, oh, is it over or under trained? You'll have a hard time discussing that without having those curves. Is the training that we just ran with the newsgroup data called unsupervised fine tuning? If not, what is the name of what we just did? So here we are with the abuse of the terms and the variance of the terms, okay? So it depends. So I think that I have seen people call this unsupervised fine tuning. I think OpenAI would call this unsupervised fine tuning. Some people would just call this fine tune. Some people would call this just causal language modeling. Some people would call this just fine tuning. But some people would call this like semi-supervised. Essentially, it is, I mean, there are different names, but I think OpenAI will call this unsupervised fine tuning. Some people will call this like domain adaptation. Like there's just like a lot, there's many words associated with this. And it's really, you have to look at the context in which people are sort of using it and what they're describing when they say unsupervised fine tuning. I think the reason that some people will call it unsupervised is because you yourself don't have to provide any label. The label is inherent in the data set, and it's just the next token after wherever you are. And some people, I think, would call that semi-supervised because you do provide a label. It's just you've already provided the label by providing the data. So it's a jargon thing.
And sometimes it's called self-supervised as well. And really, I think it kind of reflects that it's almost an ideological statement, depending on what you call it. Like unsupervised, when they call it unsupervised fine tuning, they're making the case that the data is that the model is learning directly off of the data. And they're sort of emphasizing that it's learning the structure in the data. Whereas causal language modeling sort of might obfuscate that a little bit. So it's kind of interesting why they choose to call it what they call it, but boy, there are lots of different names.
Yes, and thank you for that, Jesse. I think the term that I was looking for was self-supervised, not semi-supervised. That's something else. Michael.
I guess that's kind of where, for the training we just did, is actually we actually changed all those parameters of the GPT-2. Correct?
Yep.
I guess that's kind of where I think I read somewhere, I'm not sure exact that's the right description. For many of those fine tuning, they actually frozen the parameters, right? And only, I don't know how the new parameters are added or something. I guess that's kind of where I feel like this is not really fine tuning, right? It's just we add more data to the pre-train.
So I think it depends how you kind of look at it. So I would say, it's fine tuning in the sense that you are training your model to better reflect the specific data that you're interested in, as opposed to just any data that the model was trained on. But there are different training methodologies for training models, some of which include freezing layers and unfreezing layers. So if you were to look at another architecture called ULM-FIT, they would talk about like gradual unfreezing, where they would train like the last layer first and then like unfreeze to kind of combat this notion of catastrophic forgetting. But generally, barring very recent developments, transformers have always taken the approach of just training like the whole thing. It is because this is built upon PyTorch, you can always freeze just whatever parameters of models that you actually want. But by default, this behavior will always agree to just straight train the entirety of the model, of the trainable parameters.
And sometimes for very large models, you'll train only the head, right? So if you're really comfortable with the representation as it currently stands, then even if you have a task and even if you have some training data, you might train only the head, which is you're essentially treating the entire transformer model as a big old feature generator, right? All it's doing is generating features for you, and then you're going to do your neural net, or you're going to do some other kind of differentiable head on top of it, and you only train on the head. That's possible too, and that's a cheap way to quickly get a model trained up. Especially you might do that, especially if you're sharing that body with many different heads. So if you have multiple heads that are using that same underlying, then it's kind of a big deal to be training, and you need to have a paradigm, you need to have a scheme for training, so you don't have catastrophic forgetting. It's not catastrophic forgetting, but it is you might affect the performance of other heads. So you need to do like a round robin training. Tesla does this because a lot of their in the most recent release of the self-driving stack, they went to a single pre-trained body that was trained on both city and highway. And then they have all these different heads that do city driving, highway driving, object detection, all this stuff on top of it. And when they train, they have to go and be very careful that they don't train just too heavily on one head, because then the entire model begins to shift to meet the demands of that one head and all the rest suffer.
So, Professor Jesse, that's a great pointer. So I'm wondering, I remember the evolution where many, because of, Microsoft or Meta, they open source their Llama, and then Stanford took it and did 2 additional models on top of it.
Yeah.
I guess for that, do you foresee that? I don't understand the technical detail part of it. From your understanding, is that the Llama maintained as it is, and then the Stanford just add 2 more layers or head on top of it?
They didn't add heads. They actually did significant instruction fine tuning on top of it. So there is this deal where where Meta open sourced the architecture, but not the weights. So they needed to do additional training so they could take it from the state where it was more open, in terms of the licensing, and did instruction fine tuning. And so it was a more easily licensable solution. Well, actually, I'm sorry, Stanford for Alpaca was just showing that they could go from base model to instruction fine tuned without a whole lot of money. Then another group, because the architecture was open source, but the weights were still controlled, only licensed to academics, they redid the whole thing. So Stanford did just some training, but it was all the weights. They weren't freezing anything. They were doing instruction fine tuning on all the weights. Then Red Pajamas and other groups too did an entire retraining of all the weights from scratch, set them all to random, and then did total retraining, which was a significant amount of compute. But those models now are available for very permissive licensing, so you can use it for academic or for commercial use.
Got it. Thank you.
Laura.
I just wanted to ask a quick question about the relationship between in-context learning and fine-tuning. So is it the case that if you're fine-tuning ahead, unless you freeze layers, then that fine-tuning, that will just be lost because of in-context learning?
So mind if I answer this one, Charo?
Go for it.
Okay, all right. I love in-context learning. So, my PhD is in cognitive psychology, cognitive science, and in-context learning is fascinating to me because it is entirely different from any of the other training that we've been talking about. So all the training that we've been talking about is back propagation and actually changing of the weights permanently in the model. So when you do training like we've been talking about, doesn't matter if it's self-supervised, whatever you call it. Doesn't matter if you freeze some of the layers or if you're only training the head, it's all going to be in there in the weights because you're literally changing the weights. And if you save that model, you're going to save that knowledge and that learning, right? In context learning happens with very large models. It seems to be around 7 billion parameters or more. And where you get this emergent behavior that you don't see with smaller models, like GPT-2 does not exhibit this. GPT-3 does exhibit this, where you give it examples and problem samples and solution, problem sample solution, problem sample solution. And then the model, only in its activations, not in the weights, the model in its activations represents how to solve that problem. And then it can solve problems up until you get to the end of the context, because all this has to happen in the context. So this has to be within the span of the attention. But within the span of the attention, if you have problem, solution, problem, solution, problem, solution, then you can go to town and have, okay, problem, 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 and it will solve all of those. The minute that it runs out of context, poof, it's gone, because you're not saving that to the weights. So there's a model called Claude. Do you mind if I say this, Charo? I don't want to take a whole lot of time. Model called Claude 100,000K, which is 100K, which is 75,000 words. It's huge context, like an order of magnitude greater than the smaller models, and many, many times of even the largest models. And last week I did in context learning of a task that we were unable to get other models trained on. So we did it in context, but we were not able to train a BERT model or other models through supervised fine tuning to learn how to do this task. But I gave it 700 examples of this, and it learned it, and it was above 90% accuracy. And this was doing categorization on 18 different categories, which is extraordinarily hard. And it did it. And it did it. So this training, you saw how long this training was taking. This training was taking, certainly a couple of minutes. On the longer ones, it can take hours. It did this in 30 seconds. This is a very, very different way of learning. So we call it in-context learning, but it's entirely different from how we do training right now. When we understand exactly what's going on with in-context learning, and when we're able to convert those into weights, and so it can be stored. And this is a problem that I'm working on right now, is how do you store that learning? Once we're able to do that, that is going to entirely revolutionize everything that we're doing right now, even more. So we're not done yet. So know that in-context learning is very different, extraordinarily powerful, but is the realm of large models with long contexts.
That's super helpful. Thanks so much.
Awesome, awesome, excellent conversation. Okay, so we have finished our fine-tuning pre-training situation on our particular data set. And now what we're going to do is going to go into our supervised fine-tuning. And the way that we're going to do that is we are actually just going to grab this alpaca data set right off of Hugging Face directly. And so we can make that pretty simple for ourselves by using, and now I remember why I had load data set, because we're going to use this load data set function, and we're going to get alpaca, except we're going to do something kind of interesting with it, which is we're going to make it a data set, essentially, one single data set instead of two, anyways. So, and then with that, we're going to do our regular training test split as we've done before. And then we're going to use, oh my goodness, literally this is the same exact function that we used before. Why? It's because we're pretty much doing the same exact thing, just on different data. And so whenever we're doing our training now, it's actually reflecting, like it's the same process, but it's reflecting a different overall goal because we have these instructions and we are, the word that we predict is not just the next word, but it's the best word. The best word for the next word. So here we can go ahead and run this one. So we'll tokenize that nice alpaca data set. Exciting. You see that it kind of ran twice, that map, because it ran on the train and the test that we just split. Now our data set dictionary is called IFT token. Here, you know what we can do? So we have this GPT-2 email thing. That's the thing that we kind of pre-trained more. And now we can just save this next one a little bit separately, because now we're getting into supervised fine-tuning. So if we ever came to the point where we just kind of didn't like the supervised fine-tuning that we did, or we wanted to, I don't know, do something different, we could actually go back to this checkpoint and restore this one and keep training. So we're going to store this as a separate directory altogether. And let's call this one GPT-2 email supervised. Okay. All right, we're going to stick with steps. We're just going to make this one a little bit longer. So I'm going to go with 500, let it update. For the batch size, okay, this, I'm gonna put it to 20. I'm sure it can probably do more than that. And then I'm going to leave it to one epoch. You might not be able to get 20 in here, depending on what kind of collab you have. If it needs to be something lower, just set it to like something like 4. Here we're setting up our trainer again with actually our best model loaded, because that's what we have as GPT-2. See that there is no new creation of a GPT because we are using the one that we just trained. And we're going to be using these training arguments with our same tokenizer, same data collator, and then we're just using different data sets for our instruction fine-tuning and supervised fine-tuning, and then we're going to give it a good train. All right, so this one is going to take some time. Honestly, it's going to take time. So while we are discussing that, what we will do is discuss other things. Oh no, something was unwanted. Oh, yep. So I did the thing that I wish not to do. We're going to set this back to be something else. This is really unfortunate because actually I'm going to have to restart this, I think. Oh, cancel. It was not pleased. So basically that error that you saw, CUDA out of memory, whenever it says that, that basically means you just tried to put too much data on me. And I have ran out of CUDA or GPU memory. You need to make your batch size smaller. Usually the way that we deal with that is just to restart the kernel and then it clears the CUDA memory. But that also means that we do have to restart the kernel. So now we're kind of doing all this again. Actually, you know what? I don't actually have to do all that again. I could actually load this from this checkpoint. That's okay to do that. All right, so real quick. So Michael, question.
I guess I was trying to walk through, this is kind of where I still kind of fail to understand. What exactly the difference between this training versus the previous one we did?
So the difference between these two trainings will, in practice, or in terms of the actual steps that one does, there isn't really one. The difference is the data upon which you're training. And so then the interpretation of the behavior becomes a little bit different. So no longer are we just predicting any next token, we are predicting the next token based on instruction history or the best way that we want to phrase something or something like that. So it changes due to the nature of the data we're training it upon. It's still the same causal language model.
So where that instruction was given is in the data itself?
Yes. So if we want to, so this is the data that we nope, not that one, but this is the data set that we have. So it's this one. And you can see that we are using, so we're using this text here as what we're doing our causal language modeling on. And if we take a look at that, we see that this is the full text. So at any given time, if we have, let's say, maybe we are at this point and we need to predict the next token, give, or maybe we're here at response 1, and that's what we predict. If we're at this 1, eat, A. And so because we have all of this that we're trying to predict, we learn then how to follow instructions.
Ah, I see. Is really the data is already giving the instruction when you do the training.
Exactly.
Okay.
There was a phrase that was popularized about 10 years ago as machine learning sort of began to rise, and that is the data, your data is your source code. And the idea is that you're not doing anything different here. The architecture hasn't changed, the training hasn't changed, none of that has changed. All this changing is your data and how you're presenting it. And so and that's it. So you're getting entirely different behaviors, and the model is learning entirely different things because of what you're training on and how how you're choosing to chunk up what you're training.
I guess the thing is, at least before the large language model, what I understood for the supervised previously is like, you have the label, right? So you label your data, then you kind of compare the result with the label to see the accuracy or the recall or whatever. But here, in the language model, the instruction is not so much as labeled, but it just gives more context.
Yeah.
And I guess I really like how you just phrased that, because we do tend to call this supervised. So, I mean, it's called supervised fine tuning. And why is that? Because the answer that you want it to generate is actually given, like the true answer that you actually want. So, when you ask it, give 3 tips for staying healthy, literally, you have written those things. So I think that's why it tends to be referred to as like supervised fine tuning, because, when you have just the causal language modeling task, it really just revolves around, okay, all I care about is just getting the next token, the grammar right, the concepts right generally. But here we're targeting like specific words to be said. I think that's why they tend to refer to it as.
When you give the instruction to the large language model, do they actually parse this? Hey, I don't know. Is actually to parse out this text so that which one is the correct answer, which is the instruction.
So this is what's given to this text part. This is what we're giving to the model. when you think about how we use these large language models, we give it kind of this whole entire thing. Like we give it this instruction, the input, and then it generates the rest of this. But the thing is, like, all these things are always in its context once it starts generating these things. So we give it this whole entire thing to generate upon.
I mean, to some extent, I'm trying to understand is that when you feed that, for example, when you feed that prompt, you know, with the few shots or whatever, or in this particular case, you give the instructions, why the large language model knows to follow that instructions? I mean, because to me, it's just a paragraph, a passage of text. How does it know, okay, this is the instruction, I actually can get some sense out of it?
Remember, the transformer is a powerful general purpose learner. And that doesn't mean that it memorizes, right? It forms representations that allow it to what comes next. So remember, just by doing the mass language modeling, it learns, you know, language rules, parts of speech, semantics, it learns style of writing, you know, it learns facts, it's not doing that through memorization, it's doing that because it forms representation. So if you start challenging it with, here's an instruction, which it's seen some of, right? Just in what it's been trained on. But before it might have been trained where it had like instructions and response all together. But now you have instruction, and then it has to get the response. It's not going to do very well at first, but then it's going to learn and represent the idea of, oh, this class of things phrased in this way are always instructions. And my response now needs to be answering or carrying out the task rather than continuing. So the example that I use is give me, you know, describe some books from Zora Neale Hurston. And a large language model that's not had the instruction fine tuning will say, because I think she's a great writer and would like to learn more about her. But an instruction fine tune would say, oh, that's an instruction, and then start trying to answer that by saying, you know, their eyes were watching God. And then, you know, maybe a few others, and then it's going to begin making up stuff. But at least it's responding to it as an instruction rather than as a generalized text generation task.
Got it.
And we will also see an example of that, hopefully, after this model finishes training. Otherwise, I'll show it to you in the solutions. So as this model is training, we're actually just going to casually ease on down to this reinforcement learning for human feedback. So what we have seen, honestly, is that we have all the tools necessary. Actually, we learned all the tools necessary to do our pre-training / fine-tuning and our instruction fine-tuning, our supervised fine-tuning. We had all the tools since yesterday. Now, what about this reinforcement learning from human feedback? Okay, so that's the question, because now we need, one, we have to have this data set that has these prompts, and then also has, I don't know, somehow generated numeric ratings for each, or some sort of scalar evaluation for how good a response is, especially in comparison to another. OpenAI describes a method to do this through ranking, but other people do different mechanisms to try to make that happen. So one, we need that, but two, now we have to do like this preference modeling thing, and then we need to take our model, and then we also need to have like this PPO model, and then we need to be like comparing these, getting a reward, with like feeding back. So that sounds like sort of a lot. That sounds like a lot, and we haven't seen a lot of that in the Transformers library the whole time that we've been looking at it. The good news is that Transform, or Hugging Face, has provided some help for us, and it is in the form of this TRL library. You kind of have to just kind of go directly to it, because for some reason I can't easily find it in the documentation. This is also very like super new. No, okay, maybe not super new, but it is under development. For example, if you go to Maine is actually unreleased, but they have new supervised fine tuning classes and things like that. Okay, but so here we are in TRL. Give it a good read. It'll talk more about what you need to actually do. You are going to see a lot of this. Okay, gotta rush. You're going to see like a lot of this going through like this documentation. It's going to mirror what we saw in that blog entry, just going to express it a little bit differently. But here you can see, here we just have like this straight pre-trained language model. We have this reward model that we generate, so straight language model, and then we have this reward model that we actually generate. And then what we do is we use this language model that we have, we create a reference model from it, then we get these responses out of the model, and we use our reward model to generate this reward, and together we use that to train, we use that to get this value that we feed back to our active model. And so as you see here, we see where the computational complexity is like increasing significantly, because one, we have to create this reward model, however we decide to do that. Sometimes that's even like another copy of this language model. And then we actually have to have these two reference models. So you have to have the active model, the one that you're training, and then the one that you're doing inference on. So that's like a non-trivial amount of like work. Again, luckily we have some help to help us. So here, this actually provides us a really nice example about what we will need to be doing here. And it shows you kind of that in code form. We are not going to actually type these things, but we're going to take a look at a notebook that someone has prepared already for this. But this gives a really good example on how one would go about, or just the basic foundations of how one would go about training. And so you can see here that we import all the things we need. We have this, the model that we actually want, and we have that reference model that we talked about, and then the tokenizer. And then we create this PPO config, which we use to create our, which I mean, generally tends to contain the model. And then we have this trainer where we actually do our training based on the model and this model reference. And so then we go and generate our general training loop. If you need to look more at that, we can look at these. So here we have some of the models that we might be using. We have a trainer, so we just call trainer.train, right? There's a PPO trainer, so that's training our model for our reinforcement learning, or using our reinforcement learning, and PPO is like a method for reinforcement learning. What we're going to do is we are going to look at this example, and we're going to go through it very, very briefly, given that we have 8 minutes left. And so what we can do is we can see this example. I'm actually not going to open this in Colab. I'm just going to look at it directly. So, oh my gosh, there it is again. Something that is really interesting about this is that, remember how we talked about there has to be some sort of reward model. Their reward model is based on a BERT. So it's based on a distill BERT. And so you get the query and response, and it gives you that numeric reward. And that's what we use to train our PPO model, a part of that. And so that's really interesting that they use something completely different. Often like other organizations are talking about using just another language model. So here we see exactly what we saw before. We create our configuration. This one, this is the model that we're passing in with some of the parameters that we want to set, and we can see that in the actual API. You'll see things like WANDB. These things are about like tracking the progress of the model as it's training. Here you can see that this person actually fine-tuned their GPT-2 on IMDb, which is something that we just did. We just fine-tuned it on emails. Here you see what we have done. It's just that this is doing a lot more things to try to get the data kind of in the way that they want. So essentially, this is building their data set. You can see that they have the tokens. They set the pad token to be the end of sequence token. They're loading the data set. They're renaming some columns. They're taking some things out that are too short. Then they are making this data set into like a particular like a particular shape. And then they're doing some tokenization. They are fixing the data set so it's in the format that is actually needed. And then they create the data set type. They define the data collator, looking really familiar. Here we have what we saw before, where we have the model that we actually want to train. This is going to be our PPO model. And then this is going to be the reference model. And then, so the same could be this, it is the same one. But this is the one that's not going to be changing at all. This is the one that we're going to be training. Here goes the tokenizer. Again, we're setting that. And now we create our trainer. This is helping us to create our classifier, which is going to be generating us some numbers. And now we get into the actual training loop. I think that this will become a lot simpler as we go along. This thing right here is like a true training loop. Like this is something that you like have to write, right? And so I think that this will be simplified in like the next iteration of TRL. But for now, this is a really good guide about what to do. Essentially, it's going to be like generating this response, it's going to be comparing them together, and then it's going to be generating the reward, then doing the step. And so this is what this actual part is doing. If you want to look more into it or try to understand it a little bit better, GPT-4 can help you out a lot. Also, a debugger can also help you if you want to look at that. And so here you can look a little bit more through this, but these are also great ways to look into the data set. This is a great way to understand how your model is changing, right? So we have this reference model that never changes. So that's our fully pre-trained model that we kind of wanted. Maybe it has SFT, all that great stuff. And then we have this PPO model that we're training for reinforcement learning. And what we can do is look at that original model and look at the trained model and see what the difference is between how they are predicting. And so I think that's pretty cool to look at. That's something that we can also look at in general with our own models. And so knowing, oh man, we're not going to make it. Oh, maybe we will. No, we're not going to make it. So therefore, let me just pull up this. So here are actually the solutions. And we're just going to take a quick look at how we can evaluate. Sorry, you're getting seasick. All right. So in our notebook, after we've done our SFT, okay, we have this trained model that we want. So as we saw in this TRL, something that we can do in addition to using that compute metrics and evaluating on like a separate data set, some metrics that we want to look at, we can actually just like look at the models that we've used, right? So let's say, for instance, that we have this phrase, we're writing, I am writing a college paper on the history of oral exploration. Please write a 100-word introductory topic paragraph on this topic, okay? So we have instructions, and then we're telling it to do something. So now we can use that same inference methodology that we had. Remember when we first started talking yesterday, if you wanted to do inference, what you did is you used a text generation or whatever kind of task pipeline that you wanted, and then you specified the model that you wanted to use. We can do that too. So we're going to create a pipeline for text generation. This looks just like it did yesterday, GPT-2, except we're going to specify that this is going onto a device. So this is our first GPT model that comes off the shelf. Then we're going to use the model that we did SFT, or that we pre-trained further or fine-tuned, and we're going to load that one because we actually have saved it over here, right? We're going to load it in the pipeline, our own. And so we do same text generation, except for now, we can use that checkpoint directory as the name of the model. We're going to put that one on CUDA, and we're going to do the same thing for our model that we have finished training, which is our SFT model and we're going to put that here. Then what we're going to do, so this is a list comprehension. Essentially what it's doing is it's putting the test phrase through each of the test phrase through each of these different models, and then getting a response where the maximum new tokens to be generated is limited to 150. So we look at those responses. This is just going to print them. So now let's look at the difference. This is the first GPT, so the run-of-the-mill run that we got offline. Okay, not run-of-the-mill, but the one that we got offline. Instruction is blah, blah, blah. Please write a 100-word introductory paragraph on this topic. And then it just continues writing, following no instruction, right? And why is that? Because the initial GPT model, what is it trained for? That's right, next sentence prediction or next word prediction, that's it. That's all it cares about. Now we can look at our fine-tuned GPT. So this is the one that we pre-trained. And so now it does continue writing. So now it says, this is where our prompt ended. And it just kind of keeps writing, right? It says, please share the experience of sci-fi explorers. It would be greatly appreciated. And then it does this thing. That looks a lot like the emails that we trained it on. And so that's why it's looking more like this. This is the format of those emails. Like it reflects that a little bit better, which is interesting. So one, we see that the fine tuning worked. Here, now we get to, after that fine tune, this is the instruction fine tune. Now we have the same prompt. I am writing a college paper on the blah, blah, blah. Please write 100-word blah, blah. And then it kind of starts with the actual introductory paragraph. The following quote sums up the whole blah, 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 blah. blah, 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 blah. Now, is it crazy? A little bit, yeah. Probably needs a little bit more training. I just didn't train it that much. But you can see that it seems like it's trying to follow the actual instruction instead of just literally continuing on the sentence. So here we can see the effect actually that we have done these things. We can see the effect of our pre-training. So from this one, and we can see the effect of our supervised fine tuning from here to here. And again, go take a look at this demo code. I know that we're at the end of the time and I want to respect your time. The last thing is, I know I just said that I wanted to respect your time. The very last thing that I will tell you is that, if I could just get there. This thing here, that has a very significant impact on how your model stops generating. So once you set this pad token to be EOS token, when you use the data collator, that means all of your EOS tokens, so end of sequence, that means stop generating. All of your EOS tokens get masked out. And that's why you see it often say setting pad token to EOS token for open-ended generation, because it will continue generating literally until you tell it to stop. If you do not want this to be the behavior, the way that you can get around this is to add a token and add a specific padding token. And that, I guess that's all okay, we're at 11:01, I've already gone over time. But maybe if you want to see a little bit more of that, we can talk about that during office hours. But thank you for coming today. I hope that you learned a lot. I hope that you've had your questions sort of disambiguated between what is like this initial training and then what do I do after, and then how are they different? And now you also have the tools to be able to train your own with some good data sets to help you out. So thanks for coming today. And now I think we'll go into our office hours. Oh, and I think I see maybe a question. Yeah, I see a question in the chat, which is the code again for load data set and split for E. This one. So this is going to be loading alpaca. And that's a data set. And Raymond, did you have a question? Oh, awesome.
Yes, ma'am. When Jesse was talking about blog, I'd asked a question a while back, and my phrasing was even worse than it's probably going to be today. But what I was trying to ask him was, okay, I was basically asking him, hey, I'm horrible with 3-letter acronyms and words in general. What's a newbie way to start using blog with long context? And since my phrasing is a little bit better now, I wanted to see if he had any suggestions.
Was that for Jesse or for me?
Oh, it was for Jesse.
Okay, if you could repeat that one more time.
Yeah, a while back I butchered her question, but what I was basically wanting to know was how to use plug with long context, and my jargon is horrible in that area.
Oh, so how to use what with long context? I'm sorry.
Or basically, I would be able to use long context like full documents, and then I would also be able to incorporate plug. That was what I was trying to ask you about a while back.
Okay, and that's the part that I'm not quite getting. You could also incorporate what?
Like, it was like I wanted to be able to read and process long context,
Yes.
but I also wanted to incorporate Claude into that.
And what's that word? I'm just not getting the word. Go and
Are
put
you
it in
saying
the chat.
Claude?
Yeah, this
Claude. Okay.
is, I live off of Highway 412. So, sorry.
Okay. No, that's fine. So Claude. Okay, great. So Claude is a different model, right?
Yeah,
So you have like GPT-4, that's one model. ChatGPT is another model. Claude is another model by a different company called Anthropic. So Anthropic has a model called Claude 100K Instant, which is the one which has the very long context length. So it's 75,000 words. It's 100,000 tokens.
yeah.
And we're not exactly sure how they do it. We know some of the things that they use, but there are other things that they're doing that
Okay.
we don't understand.
Yeah, I've kind of had to do AI Summer asynchronously because 412 is 20 foot from my bedroom. So Highway 412.
Oh, okay, yeah.
Yeah, so that's why I was like, it's like I know I'm terrible with the nomenclature sometimes to begin with, and then people want to go 65 and a 45 for the last 4 weeks hadn't helped.
Yeah, no. So Claude is available. I think the only place that I know that it's available right now is through poe.com, POE.com.
Okay.
And if anybody knows anything else, that'd be great. You can get to it with a subscription. There's not an API right now that I know about that I have access to. So it is all cutting and pasting.
Okay.
To the web, the Poe interface. And it's not great because there's no easy way to scroll, which is okay when your context length are short. When your context length is like a book chapter or more, I've been wearing this wheel out. I've been like scroll. So it's not ideal yet. But that's the only way that you have access to it right now.
Yeah, and just one brief tidbit. I mean, like real person brief, not me brief. What I was trying to ask about at the start of the meeting is if there are webinars over the summer that I could participate in as a community member, I'm interested.
Okay.
But I was asking whether or not, you know how Jules currently has the prompt engineering on Coursera?
Coursera. Yeah, we've not done a Coursera yet. We will probably be doing some, but not until the fall.
Okay.
Yeah, and the issue is they require more setup, but we might switch to some of that. But frankly, we've had to I know that's kind of cool. But we've had each time we've done an AI Summer, we've had to substantially change it. So we got to look. Maybe we can, Shara, we can talk to Jules and see how much lift there is between what we do here and doing it as Coursera, and maybe pick out some like essential things that like will not be changing.
Yeah, because for like deep learning AI, just from what I've had a chance to look at, basically kind of the GPT, the hey, we just found out this yesterday kind of stuff. Some of the more static ones that are still, the things, so to speak, are kind of slow in incorporating that. That's why I wanted to make sure. And just as a small tidbit, I'm still playing leapfrog between meetings with you and Dr. Kondo, and she suggested I tried to sometime before Doomsday meet with you about that. But other than that, I don't have anything else.
Okay.
She met with me in August, and that's why I met with you the morning of November 10th. And you wanted me to read NLP for Transformers, participate in this, and then meet with you again. It was about that. But I have a meeting with Dave, and he finds me monologuing for an hour much more enjoyable than the average person. So I'm going to prep for that. Thank you. I appreciate it.
Good plan. All right, good. And thanks, Marcus. Yeah. Hey there, Ben.
I have a question.
Great.
Are the weights Llama models still available?
Well, the weights for the Llama models were never actually available. They were around, but they weren't available because you're supposed to only get them directly from Meta. Because they didn't release them. They were leaked, but they didn't release them. So, but frankly, Red Pajamas, the 7 billion parameter one is well on its way. The 13 billion parameter one, the 30 billion, they're all getting done, and they're going to be ready by this summer. So, and training is going really well with those. And they're actually being trained down the road from Nashville at Oak Ridge. So they're using some of their hardware for that training. And so when it's done, that's going to be like completely open. They're getting really good results, better results than the original Llama by being more careful with the data that they're training on. So I think that's going to be the way to go. Plus, there are other ones that are available now too. You just have to look at the licensing to see what the weights were that they started with. And with Red Pajama, that's where it's going to be like they started with like Rand. Those were the starting weights.
Well, thank you.
You're
Trying
welcome.
to see which ones I can get that can run on 16 gig or less.
Yeah, and take a look at the there are some really good libraries in Hugging Face for dealing with running running larger models on low resource, right? So I forgot what they're called, but
I think they're the PEFT with
right.
performance something.
Yeah, parameter efficient fine
Right,
tuning.
thank you.
Definitely, if you want to do training.
There's another one too. You're right. There's
Yeah.
also Accelerate.
There's Accelerate, which will do in parallel training, PEFT, PEFT, I call it PEFT, I don't know if other people call it PEFT, that will allow you to do the training, plus adapter-based PEFT is like a way to do really efficient fine-tuning. And Michael Guo was sort of getting in the neighborhood of like frozen. I wasn't going to mention that because it would have just confused it more, but that is how they do it. And then there are other libraries which allow you to do inferencing on lighter hardware. So yeah, but look through the Hugging Face documentation and information for that.
Now, I know that the parameter size is usually smaller than GPU memory, but with PCIe speeds being, I mean, I guess it depends how much of the data per run you want to be swapping.
Yeah, it does take more time, and again, it's a big difference between inferencing and training. If you're training, you definitely have to have GPU, even if you have to be swapping out the memory. You just have to have the GPU. On inferencing, you can do that on CPU. You could do it on GPU. The trick that they do is that they swap out they swap out the parameters and like do the inferencing, over, and that's how you do it if you have a GPU with less memory. So it's a neat trick, but it does take longer to run.
How do they do multi-GPU training? Do they just different components for each back propagation?
Sometimes some of them do, but you can also do something like a federated learning on your own, like local machine, where you average the weights. You do the trainings and then you average the weights, which is less efficient, but is better than trying to do it serially. So there are many different ways though, but Accelerate Accelerate is definitely a package that has all the training stuff.
And then Ben, hold on. There's something else. I'm trying to find it right quick. I'm on a different browser. Okay. There is a really nice resource Hugging Face on this. And again, I can't. I'm just gonna guess it's this one. All right. So this is just transformers. This sidebar here is like so great. This performance and scalability, so great. So it talks about how you can train on like mini GPUs, inference, whatever else you need in your life. Like they've pretty much got it covered here. And they talk about also different the ways that it's implemented in transformers, because I think they have most of these things already implemented in here, and you just have to have specific settings in training args or something like that. Then there's like these sorts of things, but then there's a blog post that I can't find. But depending on what kind of computer that you have, sorry, I'm making everybody seasick, but it's what's happening. There's this one, but I think that's not, there was something about it that didn't seem, there was something, it's maybe a different architecture or something. Yeah, I think it was AMD. I don't have an AMD processor, but if you do, then this might be a way to do it, or just read through it to see like how you can do it. But yeah, these blog posts are like the best thing ever. Is that helpful?
Yeah. Thank you.
No problem. Good luck.
Thanks. See you.
See ya.
Just us. I'll go and I'll stop the recording.